All right, so we're in 6.2 now, and 6.2 and 6.3 are going to be looking at kind of what we did at the end of the last section, which is solving differential equations by first assuming that our solution takes the form of a power series. Now, in the last section, 6.1, we ended with an example where we did that with a first-order equation. But in this section, our focus is going to be on second-order equations. And in order to do what we're doing here, we have to start with a couple of definitions, specifically ordinary and singular points, and go through the process of what it looks like solving for solving a second-order linear DE using power series centered at one of these either ordinary or singular points. And in 6.2, we're looking at ordinary points in particular. So to set the stage, we're focusing specifically on homogeneous linear second-order equations, which, again, the general form of those looks like this. And as we have done previously, we want to put this into sort of a standard form by getting the coefficient on my y double prime to equal 1. That's just going to require us to divide everything through by this a2 of x right here. That's going to take this dE and make it look something like this. Y double prime plus p of x y prime plus q of x y, where p of x is just a1 over a2, q of x is just a naught over a2. Okay? So using this form and specifically thinking of this function as p of x and this function as q of x, we have the following definition. So at any point x equals x naught is called an ordinary point of this differential equation right here if both of the coefficient functions p of x and q of x in this form are analytic at x naught. And remember, what the term analytic means is that both of these functions, p of x and q of x, have a power series representation centered at that point, centered at x naught. So we can rewrite p of x and q of x both as power series centered at x naught. If that is possible for both of those simultaneously, then we say that the number x naught is an ordinary point of that DE. If a point is not an ordinary point of a DE, then we call it a singular point of that DE. Okay? Now, let's take a look at a couple of examples where we want to identify identify ordinary and singular points. So this DE, to begin with, it's not in the standard form that we want it to be in. We want that coefficient on my y double prime to be a 1. So the first thing I would need to do is divide everything by x squared minus 1. Now I'm not going to, actually, yeah, for this first example, I'll go ahead and do this. So that's going to look like y double prime plus x over x squared minus 1, y prime, minus 5 over x squared minus 1, y equals 0. Now this coefficient right here is p of x, and this guy right here is q of x, okay? Now, looking at this, we have to figure out how are we supposed to find ordinary and singular points. Well, ordinary points are going to be points where these two functions are both analytic, which means we can find a power series for each of these. Now, with rational functions, there is an important property that we're going to use here, which is that a rational function is always going to be analytic at any point in its domain. So, for example, both of these functions are defined for x equals 2. If I plug a 2 into this, I get 2/3. If I plug a 2 into this, I get 5/3. So it's defined there. That law, that property that I just mentioned, guarantees that both of these functions are also going to be analytic at that point. On the flip side of that, these functions will not be analytic at any point where they're not defined. And that's actually true of any function. No function is analytic at a point that's not in its domain. So really, the question of identifying ordinary and singular points boils down to just finding the domains of these functions. So the singular points for these two functions are exactly the zeros of the denominators, because those are going to be the values for which neither of those functions are defined. And that would be x equals plus or minus 1 in this case. The ordinary points are literally everything else. Or equivalently, x is not equal to plus or minus 1. So all the real numbers except for plus or minus 1. Those would be ordinary points for that. Okay? Again, in the case of polynomials or rational functions or a lot of the familiar functions, exponential functions, logarithms, things like that, the question of identifying ordinary and singular points mostly just boils down to looking at the domains of those functions. Let's take a look at this second example. You'll notice the second example is already in the form that we want it to be in. My coefficient on my y double prime term is already a 1. So that means p of x is 8x cubed. Q of x is negative e to the 2x here. Both of those functions are defined everywhere. And polynomials and exponential functions, like we said, have the same sort of property as rational functions. They are defined everywhere, which means they will be analytic everywhere. So there are no singular points here. And the ordinary points are all real numbers, all reals. Okay? So this first example is an important one because it kind of illustrates what we're going to be doing a lot of in this section. Suppose you're given a DE, a linear second order homogeneous DE like this. To put this thing in standard form, we divide through by a2, like we said before, which means p of x is equal to a1 of x over a2 of x, and q of x is equal to a naught of x over a2 of x. Okay? Now, in this section, we're primarily interested in functions or DEs of this type where those coefficients are polynomials specifically, which means that both of these functions would be rational functions. And in those cases, the singular points of those functions are exactly the zeros of the function a2. And this is true even if this division causes terms to cancel out. Even those terms that cancel out will produce singular values. So you actually don't want to do the cancellation here if the goal is to find singular points. Okay? Another thing that's important to point out here, and we use this fact, is that even though the solutions to the functions that the solutions to the DEs that we're finding are always assumed to be real valued functions, it is possible for a DE to have complex singular points. Okay, so for example, this DE right here, x squared plus 1, y double prime plus y equals 0. The singular points of this thing will be exactly the zeros of this coefficient function, and those zeros are plus or minus I. Okay, even though we're not using complex numbers in the domains of our solutions, they can be singular points for a DE. Okay, and we need to use that fact, which I'll show in just a moment here. So now we're going to look at a theorem that we are not going to prove. We're not equipped to prove this in this class. In fact, there is a lot of theorems that we talk about in differential equations that we just cannot prove in this class. They require more math than we get into here. But we will take advantage of it. So this is a theorem that justifies the work that we do because it guarantees under the right conditions that a DE can have or will have a solution that can be in the form of a power series. Okay, so this is what the theorem looks like. If x equals x naught is an ordinary point, which we just defined, of the differential equation, and it says 1, what it's talking about is this guy, this kind of general DE right here. If x equals x naught is an ordinary point of that linear second order differential equation with, well, it doesn't even need to be polynomial coefficients, it could be anything. Then we are always going to be able to find two linearly independent solutions in the form of a power series centered at x naught. The reason the two linearly independent solutions is important is because it's a second order equation. And remember, the general solution to that is going to be a linear combination of two solutions, two linearly independent solutions, or a fundamental set of solutions. Okay? So this is what that series might look like, and notice this power series is centered at x naught, that ordinary point that we specified here. a power series solution converges at least on some interval defined by this, x minus x naught in absolute values less than r, where r is the distance from x naught, our ordinary point, to the closest singular point. Okay? And this is actually the reason why we need to consider complex singular points as well, because it plays into this theorem as we're about to show. All right, then this little blurb right here, a solution of that form, of that power series centered at x naught, is said to be a solution about the ordinary point x naught. And the distance r that's mentioned right here is called the minimum value or lower bound for the radius of convergence. So we're gonna do an example where we're given a DE, second order, homogeneous, linear, polynomial coefficients, all that stuff. We're not going to solve this here. We just want to identify that minimum radius of convergence that's mentioned here, okay? And we're given a specific ordinary point, x equals 1. Notice for this function, for this DE, if we want to identify singular points, then we need to, like we said before, take this coefficient function, x squared minus 2x plus 10, and find its zeros. So I'm going to do that first. X squared minus 2x plus 10 equals 0. Now that does not factor nicely, so I'm going to go straight to my quadratic formula. X is equal to 2 plus or minus the square root of b squared, so that'd be 4, minus 4ac, that's 40 in this case, all over 2a, which is 2. This becomes negative 36, which has a square root of 6i. Reducing that down, I get x equals 1 plus or minus 6 over 2 is 3i. Okay? So the singular points for this DE are both complex. We still need to use that fact. So if you remember how we looked complex numbers in the complex plane, we can graph them, right? Where do 1 plus or minus 3i live? Well, this is my real axis, and this is my imaginary axis. And the point 1 plus 3i, I would find 1 on my real axis, 1, 2, 3. 3i on my imaginary axis, and that would be the point 1 plus 3i right there. In the for the conjugate of that, 1 minus 3i, I find negative 3i, and it would be this point. 1 minus 3i. This was not drawn very well, so bear with me. What is the problem now asking us to do? Because this is a graphical representation of the singular points for this DE. The problem is saying find the minimum radius of convergence of a power series solution about the ordinary point x equals 1. So that x equals 1 is the x naught that's being referred to here. It's the ordinary point that we're talking about. And this r here that we're being asked to find, that minimum radius of convergence, is defined to be the distance from our ordinary point 1 to the closest singular point. Where is 1 in the complex plane? Well, it's right there. Being a real number, it lies on the real axis. And we are looking for the closest distance between that number 1 and either of our singular points. Now, in this case, the distance from 1 to either singular point happens to be the same. They are aligned vertically in this case, and from 1 to 1 plus 3i, I can see that that's a distance of 3 units. Okay, so that means r is equal to 3. That's my minimum radius of convergence. Okay? If it didn't align vertically, for example, if we were looking for the distance from 0 to that point, then I'm looking for the absolute value of a complex number, and we use distance formula. You would just apply distance formula as you would to points in the plane to solve that. In this case, it just worked out a little bit easier. Okay? What we have done so far has given us enough tools to start finding power series solutions for DEs about ordinary points. We don't have the tools yet to find solutions centered at singular points, but that's what we do in section 6.3. 6.2, our focus is on just ordinary points and finding power series solutions centered at those. We are going to do a few examples of that starting in the next video, and it's going to mimic what we did at the end of section 6.1. But that'll be part 2 for us.